So this is the solution for the problem Decode Ways. It's a medium rated problem, however, it relies on two simple observations. These two observations are not really hard to find and are just basically handed to you on a plate. We're going to talk about that and a more visual approach to this problem, but first, let's talk about the problem itself. We're given a string, and this string consists of digits. Pretty simple. Uh, The goal of this question is to enumerate and return the number of possible decodings of the given string. Now, what does this mean? This means that there can be multiple possible ways to interpret the strings. In language and in general, the same word can mean different things in different contexts. The same sentence can mean different thing in different contexts. It's a way you interpret and break those words apart that really matters. In a case like 11106, you have 11, 10, and 6 as one possible split. However, this is not the only interpretation. Look at the case of 1, 1, 10, and 6. This is also a valid case. Now, by the way, these valid and invalid are determined by this here, which says that A maps to 1 or 1 maps to A for us, and 2 maps to B, or 26 maps to Z. If there is a possible valid mapping, then we're good to go. So 1 maps to A again, and then 10 maps to a particular character, 6 maps to a particular character, so on and so forth like that. This brings us to the first observation. It's really simple. Again, as I said, it's just handed to you on a plate. These splits can either be of consisting of 2 digits or 1 digit. Forget this 10-6 and 1-10-6 part right now. Look at 1 and 11. Just 1 and 11. These are the only two possible cases that could ever happen given this string. You're either taking the first digit or the first 2 digits. That is it. Now, this also brings us to our first problem. Even when you have split things like 1 and 11, how do you know if that path will work out or not? How do you know one has some valid possible strings, valid possible decodings later on? You don't know right now. And this is where we'll bring in the notion of recursion. We'll just take this idea of 1 and 11 and then we'll go on continuing with the same idea for all of the remaining cases. So one had now, so we'll first consider this one right now. Then we have a decision to make. Either we consider one again or another 11. So we write both of these cases again. Again, at this point too, we still don't know what's going to work out and what's not going to work out. But in the very next case, something interesting happens. See, you have one here, one here, and you have considered both of all of these three ones. The only thing that is remaining and is in your focus is 0, 6. Now 0 as its own single digit is not a valid case. That's because the numbers are given from 1 to 26 both inclusive. 0 is not one of them. So 0 on its alone is not a good idea. What about 0, 6? 06, as the question also says, is different from 6 and is not going to be valid. So this is a case where we can simply say that this is not a valid case. Let's just stop recursion right here and we'll return home with empty hands. Not too bad, because now we can go back here. 11 has no other possible children, so we'll again go back with a count of 0. Empty-handed, so the count is still 0. But what about this now? We've considered this one here again, and now instead of considering another one, we're going to consider 11. Sorry, we're going to consider 1 instead of 11. So 1 and 1. Now what do you see? We have these three characters remaining. Now again, we make a decision whether to have 1 here or 1, 0 here. Of course, you can pick 1 and then you'll have that case again of 0, 6. That's why I haven't mentioned it here. But what if you consider the case of 1, 0? Now that is a valid case. And what happens then? The only thing remaining is 6, which is also a valid case. And so this blue marker says that, hey, we've reached the end of the string. And that means that it's a good sign. We have found a perfectly valid string Because the only way you can reach this particular point is by saying that all of its previous parents were also valid. And so this will return the good information here, and this will return here, and this will return here. So we're back at 1 with the information of there is one possible path from 1, which is a good sign, which is a valid count, which is a valid decoding of the original string. Now you can do the exact same logic for 11 as well, and this is the entire solution. Based on what? Based on two ideas. Either you take 1 digit or 2 digits. Again, it's 1 to 26, so you either take 1 or 2 digits, and then you recurse all the way through. At any point of time, you don't know what's the future, so you just recurse. Nothing to worry about. Cool, let's actually code this up, and we'll have a recursion function. And I'm going to mention it and start it from start. This is going to be an index. You could alternatively also pass these entire chunks of strings, but that's just extra overhead. We can not do that and just have indices instead. So at the end, what you want to do, you want to return the recurse starting from 0. And the start is where we'll have our core logic. What's the base case? The base case, as I described here, is the case when we can reach the very end. If you have reached the end, then that's a good sign. If you've not reached the end and you have to stop midway through, then we don't add any counts. So only when start is greater than equals to n, then we've reached the end, which means that the count has to be increased by 1. What if it's not a case? What if it's a middle sort of case, somewhere in middle here? At this point, we have to focus on this. We either take 1 or 2 digits. Let's store them as 1 and 2 here. Okay, what now? We want to say, hey, is it that the string of the start to start plus 1 is the current character in a valid range? Is it a single digit character? So we'll start from 1 to 9. If that is in the range, then hey, that's good. What do? We call the recurse again. This time with start plus 1. Look, we don't actually care about these strings, whatever it was. Maybe it was 6, or maybe it was 7, or maybe it was 2. We don't care. We just care about the counts. And so we'll just pass on this counting function, and we'll have it return in the variable 1. Simple. Okay, what about this? What about it's a 2-digit case? In this case, we'll start from n. Do the same logic. We'll start from s, start, and then go to start plus 2. And then when will we stop? It's a 2-digit case which ends at 26. So we'll include that. And now we'll say 2 equals to recurse from start plus 2. At the end of this recursion function, we just want to return 1 plus 2. Both of these cases separately and their summed up value. This is almost the solution. There are two things remaining. First is the fact that this recursion is going to be heavy. At each point of time, you're going to make two decisions, whether to take the first character or the first two characters from any given starting point. Now that does not sound very good, because at each point of time you're making that binary decision, which means that the order can go to the bar n. Ouch, right? It's not a good idea. What you can do instead is have a cache, and we'll set LRU cache as 9. What this basically allows us to do is say, you know what, we don't actually even care about the strings, we just care about the index corresponding to the count. So an index of 0 may have some particular answer, and an index of 5 may have some particular answer. If that happens to come up again in some time in the recursion, then we already have it cached. We're done. So caching is a good idea, which basically converts it from a recursion to just a DP problem. We've memoized the answers. Okay, there's another small implementation level detail. We don't always want to do this start plus 1 or start plus 2. When do we want to do that? We want to do that when start plus 1 is less than equals to n. Okay, now it should make sense. Why are we doing this? Because we don't know if there are one characters still remaining, or if there are two characters still remaining, or if there are more characters remaining. What if we are at the character, let's say 10? At that point of time, in the case we are at 10, we want to make a decision of whether to include the next character after it or the next two characters after it. But the next two characters don't exist, only the next character does. So we'll have to have that additional logical check. And I'm fairly confident this will work. So let's do a run here. Okay, n is not defined. Okay, n is the length of the string, and we'll just submit this. So as I discussed, the time complexity is going to be order of n. It's not submitted, by the way. The time complexity is n because even though there are 2 to the power n total possible cases, uh, we've cached it right here, which means that the order of time, the time complexity is just going to be order of n now. What about the space complexity? In the worst possible case, the stack is going to have one character, one, so on and so forth, all the way up till the very top. This still means that the maximum height of the stack is going to be order of n. And so both the space and time complexities are order of n, and you can see the runtime in the memory here. Cool, that is it for the solution of Decode Ways. Thanks for watching.